Now let's look at a third approach, where I have an infinite plane of charge. Well, let's say that the xy plane is an infinite plane of charge. Now for this case, I'm going to make a surface. And here's what's funky about this surface, is that as long as the sides are perpendicular, where that happens to hit, the plane and then continue on to some point below the plane, all that's really important is that that pillbox, whatever shape it has, and maybe it'd make more sense if I drew it in a more straightforward case where I have some surface that comes down, hits the plane, and then passes through it. As long as these all have the same area, that turns out to be sneaky, because at each case, the electric field for a plane is equal to epsilon naught eta, the charge per area, over 2 times epsilon naught. So, no matter what this is, that first off, I've got 3 sides. Side 1, side 2, and side 3. So, the integral over 3 sides is equal to the integral of E dot dA over side 1 plus the integral of E dot dA over side 2 plus the integral of E dot dA over side 3, and side 2, the shape of the pillbox can be as goofy as you want it to be, because the flux through that side, through the side that's going through the plane, that surface, that flux through that side is going to be 0, because the electric field lines are coming straight out from the plane, and therefore the flux through side 0, through side 2, must be 0. Now, the same way that we had it before is that the electric field through 1 and 3, in both cases the electric field is perpendicular to the surface, so E dot dA is just the integral of E dA, and the electric field at a constant distance from the plane, actually the electric field anywhere in space will be constant. So I just have the electric field times the integral of dA, or I have that the net integral, the integral over the closed surface of E dot dA is equal to the electric field eta over 2 epsilon naught times the area plus 0 minus negative. E dot dA, there, E is going in the negative direction compared to surface 1, but so is dA. So that stays positive. Eta over 2 epsilon naught times A. But now, the eta is the surface charge density. So that's Q enclosed divided by 2 epsilon naught A times A, cancels out, plus 0 plus Q enclosed divided by 2 epsilon naught A times A, cancels out. 1/2 plus 1/2 is 1. So again, the third time in a row, I find that the integral, if I take the integral over the entire surface of E dot dA, that integral is equal to the enclosed charge divided by epsilon naught. So, final answer, what Gauss's law says and here we demonstrate instead of prove it these 3 times, but it says that if I were to take the integral over a closed surface and integrate the electric field over that closed surface, the result is the enclosed charge divided by some constant, epsilon naught, that depends on space. This will come back to be important when we talk about magnetism.